Thanks very much, Steve, for the introduction, and thank you to the conference organisers for inviting me. A little bit like yesterday, like Stephanie, we're kind of an end user for a lot of the technologies and techniques that you all develop, and so I'm going to talk about a specific problem, but along the way I'm going to kind of give you some sense of why we need you and what we're looking for. So Steve mentioned I'm from the National Radio Astronomy Observatory. This is our mission statement. We provide world-leading telescopes, instrumentation, data and expertise. We train the next generation of scientists and engineers. We try and improve the inclusion and diversity of the scientific endeavour. And we promote astronomy to foster a more scientifically literate society. So, perhaps a fundamental question that comes up a lot of the time is, why do we do astronomy? Why do governments around the world invest in astronomy? So there's a couple of standard answers. There's kind of the historical, cultural one. We all are trying to understand our place in the universe, and so throughout history there have been sort of astronomical endeavours. Cosmic laboratory, when you look out into space, you see places that have gravity and magnetic fields and densities and temperatures and so on that are not possible to reproduce here on Earth, and so you can learn about physics by looking at these places in the universe. A big one is technology development. To make these sorts of observations, you've really got to produce equipment that's incredibly sensitive. And that's where we kind of push all of you in terms of digital signal processing and the other sorts of things that you're all involved in. We really very much are pushing the edge of technology. We used to push a lot harder in computing. The data that we were moving around was incredibly significant. That is still true in some ways. But a lot of it these days is digital engineering. We're actually just moving a lot of bits around and trying to process them. And so that's where I think some of the work and some of the things that I've seen here over the last few days is relevant. There is a huge difference in sensitivity. So if I was to take all of you now and transport you to the surface of Pluto, in the few remaining seconds of your life, while your cell phone was still working, your cell phone would be a very bright radio source to my radio telescopes. And the typical unit we use is 1 Jansky, which is 10 to the minus 26 watts per square meter per hertz. And so that is something to think about, particularly as I sort of move into RFI, that your cell phone, or typically 1 watt cell phone, on Pluto, from here, looks like a very bright astronomical source. And so there's, 100 people in the room here. You would be one of the brighter radio sources in the sky, briefly. And then STEM interest. Astronomy is a fascinating thing. It's a bit like dinosaurs for kids. It is a great way to get people kind of engaged in the scientific endeavour and just thinking about the world and so on. So this is why we do astronomy, and you'll notice that NRAO's mission statement kind of reflects off these topics in many ways. Talking about our instruments, this is the sort of the landmark instrument. This is the Jansky Very Large Array. This is 27 antennas on a Y-shaped track in New Mexico. This was built in the 1970s and the early 1980s, and it really is the premier radio telescope in the world today. It's incredibly flexible. And, it has these long rails because we can move the antennas around. Kind of not going to explain that today. But just in general, the VLA, you can see, is on a lake bed, essentially, and surrounded by mountains. And that's important. And we'll come back to that later in terms of why would you build a telescope in this kind of remote place with certain characteristics. This is the Very Long Baseline Array. This is 10 antennas distributed across the US, with an antenna in Hawaii and also an antenna on St. Croix in the Virgin Island. Fundamentally, the resolution of these instruments, the angular resolution on the sky, depends on the separation of the antennas. And so you can have all the antennas together, like at the VLA in New Mexico, and you just fiber the signals back. It was waveguide originally. If you want more resolution, you move the antennas further and further out. Eventually a river or a mountain or something gets in the way, and it's not simple. And certainly, 20 years ago, it was not simple to bring those signals back. So what we actually do is in each one of these antenna stations, we have a very high-speed digital recorder. Used to be tapes, now it's just disc. And to make sure that we can line up the astronomical signals to correlate them, we have an atomic clock at each one of these stations, and they write a very accurate timestamp into the data stream. We bring all the discs or tapes back. We'll kind of line them up on the basis of the clock signals and then hit play. And then it looks like they're all coming out of a a bank of fiber or something like that. So this is very long baseline interferometry. Interestingly, these days, we do fiber the data back. We can't fiber our full data rate back at the moment, too expensive. But, they are sort of connected element in that sense. But it doesn't work the other way. We can bring the digital data back, but I'm sending the signals back and forth on commercial networks. So I can't send that time standard out because you're passing through other people's oscillators in some sense. You can't line up the signals that way. So you have to have the atomic clocks out there. So we haven't removed that requirement. And that is actually very annoying. This is the Atacama Large Millimeter and Submillimeter Array. This is at 16,500 feet in the Andes Mountains of northern Chile. So, your cell phone is receiving at a few gigahertz or something like that. This telescope observes at a few hundred gigahertz. And so when you go up to those frequencies, water vapor and oxygen in the atmosphere absorb and distort the radio signals as they come down. So you've got to be somewhere that's high and dry. And so this site in northern Chile is pretty much the highest and driest place on Earth. The South Pole is actually probably higher and drier, but hard to work in. So this is a telescope that was built. This is the ALMA telescope. This was built in the 2000s and early last decade. And this is the Green Bank telescope. This is a 100-meter diameter telescope. It's a single pixel. Those other images, those other telescopes I showed you were interferometers. They build multi-pixel images of the sky. Green Bank is like having your cell phone camera is one pixel. It's a great pixel, but it is one pixel. And so you don't really image. It's much more about spectroscopy and detection and other things and so on. So this is about 2.5 hours drive from here. And you notice again, it's in a valley surrounded by mountains. That's the second clue. So what is in a radio telescope? Typically, there is some kind of antenna. This is one of the ALMA antennas. The radiation from the sky comes from the right, kind of bounces off the main dish. Can you see my mouse? Yes? Yeah. Bounces off this subreflector and then down through this hole in the surface of the dish. In there is a cryogenic system, a dewar. And so what we do is we cool our electronics down to 10 degrees above absolute zero and so on to improve their sensitivity. And we typically get a factor of two out of doing that. So it's an important thing, although running these cryogenic systems in the desert on a mountain and so on is quite difficult. It uses a lot of power and it's a lot of complex electronics in the field. Inside that dewar is something that looks like this. These are the different receivers. And so you can kind of see these sort of circular cartridge-looking things here with little mirrors on top of them. Those are the actual receivers. And so what we do is, if you want to look at a certain frequency, you kind of point that receiver through the optics, and that's how we're receiving it from the sky. So as I said, you can see kind of the container this is in. That's the cryogenic dewar that we have the receiver in. After this, the signals are digitized and sent back to a correlator. So in the case of ALMA, for example, we have 66 antennas, and each of those antennas is producing about 120 gigabits per second. So we optically fiber that back, and we have about 1,000 kilometers of fiber up on the ALMA site, which is only 10 kilometers wide, and we send it back to this correlator. So these correlators are supercomputers, maybe not in the sense that we kind of traditionally think about it. They do one thing, which is to cross-multiply the signals, the digital signals from the antennas and every baseline pair, basically. So, if you add it up, it was a 17 petaflop machine, and it was built, started building in 2004. So it doesn't really traditionally appear on any computing list, right? Because it doesn't, in practice, it can't be used to balance your checkbook or anything like that. But, it was quite impressive in its time. It still is. We're about to start building a second generation one. So it's inputting these 60, 64, 66, 100 gigabit per second links. This was all built with 2004 ASICs. It was about 150 million processors in this thing. So it sips up at the high side, and that's another problem. You've got this very high-speed digital computer up there that generates a lot of power, a lot of heat, and you're actually up at 16,000 feet, so you don't have a lot of molecules to bounce off it to cool it. And so these are the sorts of challenges. This is how our application tends to drive things along. And this is what we do. This is the radio sky. So it kind of looks like the night sky. If you glanced at it, you'd say it's the night sky. but it's not. You know, when you look at the night sky, you're typically looking at stars that are within, you know, a few hundred light years of the Earth or something. Nearly everything you see in that diagram is a galaxy at a much greater distance. And so that's one of the big differences between optical and radio astronomy. We are typically looking at radio emission from galaxies, not from stars. And so all this sort of background star-like looking thing, these are all galaxies. Sometimes these galaxies are sort of interesting. They have these large lobes. And then there's kind of this pattern that runs left to right and up and down here. That's actually the plane of our galaxy that also gives off a lot of radio emission. And so, you know, this was the joy of radio astronomy as it was developed in the last century or so, is really kind of looking at the sky in a different way, and you're kind of looking at objects in different sort of energy regimes. And so there have been lots of great radio discoveries, the cosmic microwave background, quasars, gravitational lenses, masers, dark matter, et cetera, et cetera. And so, you know, the hopeful radio astronomy student can get a Nobel Prize. It's been very productive over the course of 90 years now. So just to give you some examples, this is the radio emission from the center of our galaxy. The galaxy is kind of tilted, you know, sort of top left to bottom right. What you're looking at here are supernova remnants. These are it's a radio emission given off by stars exploding. The bigger ones are older. In that sense, the shock wave is moving out further. There are these interesting structures you see here, sort of these linear structures. They're magnetic field bundles that are somehow or other moving through the disk of the galaxy. We can blow that up. We can increase the size of the array and drill in on some of these paths. If you do that and you continue to do that with a VLA increasing in frequency, eventually what you can get to is this white dot here. And, you know, so that white dot is right down in the middle of all of this, and eventually we can resolve it down to find that thing. And that white dot is the center of our galaxy. There is a supermassive black hole sitting there. There are stars falling into it. It gives off radio emission because of that. And so recent press releases you see where people have continued to use VLBI, long baseline, to really get in there and try and see the shadow of the black hole. You know, this is sort of the progression of radio astronomy in terms of technology over many years. This is a nice ALMA result. This is looking at a star about 140 parsecs away, so 300 light years away. What you're looking at here is sort of the dust that the dust and the gas that the star forms around. And so you can sort of see the star in the middle here, and then you see these channels around in the disk. This is where planets have formed, and they basically eat the dust as they start to orbit and gravitationally, you know, sort of attract all of the dust and the gas material. The interesting thing with this one is the scale is very different. This yellow dot in the center here is the size of our whole solar system. So this is much larger than our solar system. And so, you know, really what you're looking at is the birth. The star is probably not too different to the sun eventually, but you're looking at sort of activity on a much larger scale. And this is the famous black hole shadow in M87. This is looking at one of those radio sources in the background that I showed you. If you can get enough resolution on it and you look down in the core where the supermassive black hole is, you can actually see there's this disk of material. The theory here is the disk of material is sort of the orange stuff, and what you're seeing here is the material, basically the light that's been eaten by the black hole that sits in the center of that disk. Although the jury's not completely out on this, actually. So, you know, that's what we do. And, you know, those are sort of some of the typical results. As I mentioned, the technology is, you know, largely digital technology these days. And so we've had a long history over the course of the, you know, radio astronomy's progression since the 1930s of situating radio astronomy instruments in sort of remote or very highly controlled environments to sort of minimize their impact. As I said, if your 1-watt cell phone is a very bright radio source on our scale, then your refrigerator is much worse, and your television and all of that. So even by the 1950s, when the US was building a lot of telescopes, or starting to build more telescopes, it was already very apparent you had to be in quiet areas. And so there are areas like where Green Bank was, the National Radio Quiet Zone. When the VLA was to be built, they did a US survey to find a quiet place. And you really do want that kind of general idea of being distant, and you want to be kind of surrounded by mountains is good. But of course, you know, that's set against the change in all of us, the change in society in terms of interfering technology. cell phones in the 90s, and now it's everything. Bluetooth, Internet of Things, and satellite constellations and so on. And it's a very complex problem. It's very complex for the interferometers. It's not as simple as, radio source, radio telescope, you can work out what the impact of A on B is. What you've got to deal with is the fact that the radio telescope is operating very complex. It's looking in a certain direction. It has all kinds of natural oscillators in it and so on. So exactly how it will pick up and see this radio source is very complex. There's also bounces off other objects, there's multipath problems, all of that kind of thing. So in general, this is an area that we don't really deal with. The forward gain of the antennas is so strong, 80 dB I think it is for the GBT, that we are really looking in that direction. And a local bounce off something can impact us at some level, but we tend to try and work around it. We have not got very aggressive about trying to deal with it. That's probably a mistake, actually. So this multidimensional problem in frequency and time and space and polarization and so on is a problem for our very highly sensitive radio astronomy receivers. There's two types of observation we do. There's sort of what we call continuum, where we're looking at a slab of spectrum, trying to catch as much energy as we can. And so some of those images I showed you are continuum observations. Their sensitivity depends on how much clean bandwidth we were able to observe, versus spectral line, which is where, if you look at atoms and molecules, they emit at a very particular frequency. And so if GPS is sitting right on your frequency, you are screwed. There's nothing you can do. And so what we deal with is trying to find the balance between what we want to do scientifically and what people are doing in society. And so what happens, for example, with GPS, the GPS bands, is that you just give them up. That we don't do certain types of observations in those bands anymore because, the societal need is strong enough. And so, there is this sort of general interplay that goes on between the science community and the people that are responsible for this, which is largely the ITU, the International Telecommunication Union. So, I think all of you in the room, or many of you in the room, probably deal with this at some level. The frequency space between sort of 0 and 270 gigahertz, I think it is at the moment, is allocated. There is an international agency that deals with it. There is the FCC and the NTIA in this country that deal with it, and allocations are made. And so deep down in this chart, there are allocations to radio astronomy. But this is an imperfect system, right? Because technology changes. And so we're all kind of aware that there's a lot of interest in sort of gigahertz and hundreds of gigahertz transmissions and so on. Now, there's essentially very little regulation at that point. It was all kind of focused around a few gigahertz because that's where all the action was for so long. So this table is good in the sense that it's, it is a way for us, the rules of the road, we can all operate on the road at the same time. It doesn't necessarily support scientific endeavor. So coming back to this point, if you have a radio telescope and some kind of transmitter, spectrum protection is critical if you're sort of relatively close. And so tens to hundreds of kilometers. I want to observe in this band, you guys are transmitting in some other band. As long as it's relatively clean and separated, we're probably okay. But that falls down when there are multiple applications and multiple users, multiple transmitters and so on. So as I said, typically what we have done is we seek geographic protection. We put our radio telescopes in remote areas surrounded by mountains because you get a lot of natural shielding that way. So that worked pretty well for a few decades, except that then satellites came along. And so then you're looking at a transmitting source that's anywhere between a couple of hundred kilometers and 37,000 kilometers above you for geostationary sources. And so that is a problem. And there are certainly applications like GPS where, there's basically unusable band for us now. We can't really easily observe. But even then it was not so bad in the sense that, a lot of the satellites are quite directional by design. And also, as I mentioned, if you're not looking at the satellite, if the satellite is over there and I'm over here looking over there, the impacts might be quite tolerable in some ways. Well, of course, that's sort of blown out of the water by constellations. And so there is this amazing thing going on in the country not in the country, around the world, about building these satellite constellations. And the goals initially were to sort of, produce global internet, which is, an amazing goal, really. More recently, it's now, they want to be able to use, they want to text, your phone will be able to text one of these satellites, very low bandwidth communications and so on. So that's all cool, but in some sense, each one of those steps represents a bit of a challenge for radio astronomy. And so, we've been sort of keeping an eye on this. This has not been a secret or anything. These companies have been coming at us, developing for decades, really. There have been some long-standing issues. Iridium was very exciting for us back at the turn of the century. GLONASS was the Russian GPS, the geostationary belt. We have observations which, we try to avoid the geostationary belt because it's got a lot of RFI in it at some spectrum. So we have kind of dealt with this. And, I think as a member of society, you've got to find balance. That it is not appropriate for radio astronomy to say that global internet is impossible, right? If you stand in front of that, they're just going to go over the top of you. You have to find a way to work, and you have to sort of technologically assess the challenges. These new systems that are being discussed, like Starlink and OneWeb, and Kuiper is the Amazon one, they are talking about more transmitting objects. The most amazing numbers are like, if I was standing at the VLA site, there would be 300 Starlink satellites above me. Most not looking at me, not transmitting in my direction, but that's quite amazing. So we kind of deal with that, but you have to sort of deal with it realistically. There is no business model on Earth that's going to support hundreds of thousands of satellites in the sky. I don't really believe that's possible. We'd all have to have our own satellite, basically. So, in some ways you have to sort of deal with the technological impacts of it, deal with the societal benefits of it, and the answers are technical. And so we continue to kind of look at that. In a lot of cases, these organizations are transmitting in their assigned bands. And so in some sense, why do they have to deal with this at all? Well, what it kind of comes down to is sort of the edge cases. So, there's one place in particular where we have a radio astronomy band right next to a satellite downlink band. And so if you can build a filter that looks like this, well, life is good. You're very clever. And we can build filters that look like this. They are wickedly expensive. And so that's what you kind of get into, is that in reality, they build filters that look like this. And so the very low out-of-band emission here, the roll in the filter here, puts just enough signal into our band that violates the ITU regulations. And so they then can't get an operating permit. And so they do analyses that look like this, where, given their transmitting characteristics, we look across the whole sky, and they kind of admit that, if you look down here, essentially at sort of the band of satellites, given the way their orbits run, there's a place where the observations are not going to work very well in their band adjacent to their transmit band. Most of the sky you see is sort of blue, and there's not really any data loss and so on. So we produce a lot of diagrams like this, and we analyze what the impacts are to the radio astronomy mission. And on the basis of this, we make decisions about what kind of permit and what kind of use of the system we're going to collaborate on. So the consequence of these analyses, for example, is that SpaceX and OneWeb agreed that they couldn't use their lowest channel of 250 megahertz. So that's difficult, right? We all know how much they're paying for that spectrum, and then they can't really use it because they're rolling slightly into our band. And so I think that, that presents a challenge for them, and I kind of look at it and I don't think it's particularly appropriate either. We're interfering with commerce for a band that honestly I don't think, we don't use in any particular way. And so this is, again, where this sort of collaboration between what do they want to do, what technologically is possible, what do we need scientifically, and so on. This is where we kind of entered into collaboration, in particular with SpaceX, to explore it. So we started doing tests. This is a SpaceX user terminal. This is the uplink in some ways. And so you can see the VLA in the background there. And so what we were doing were tests of, we would sort of set this user terminal down, Starlink would communicate with it. Their system's pretty impressive. You get 300 megabits per second to this antenna. Pretty impressive. But we would look at the interference associated with both the downlink signals to eat this guy, to feed this guy, and also the uplink signals, which are in a different part of the band, as it turns out. And so, we started doing experiments last year. We did the same thing. That's, if you can see the little white dot there, that's the 100-meter Green Bank telescope in the background here, and this is the user terminal, which is only that big, so this is not to scale. But what we were doing was moving these user terminals around with respect to our radio telescopes. We'd do some data transfer up and down in the Starlink system, and we'd see what the impact on our observations actually was. And so what does that look like? Here's two examples. These are two baselines. So this is two pairs of antennas on the VLA, frequency across the bottom and time running upwards. And so what you see, the little yellow sections there, that is the Starlink system trying to find someone to talk to on the ground. And so what we're actually seeing is, SpaceX's system trying to communicate with the user terminal on the ground. And we knew exactly where, and we knew exactly how long and so on. So it's pretty straightforward for us to go back into our signals, and we were sort of, I think, just observing a background source in a random piece of the sky. It's easy for us to go back and look in our data stream and see, could we actually detect the satellite? And to be honest, it was hard. We had to really know exactly where they were. And so we started doing these tests, and you sort of did different responses. One of the interesting things in this diagram is that, as I mentioned, this is essentially a triangle of antennas. And the one on the left is this baseline, and the one on the right is this baseline. And you notice they didn't see each other's signals. And that's sort of interesting. The antennas are looking in the same kind of general region of the sky. One pair of antennas saw a satellite over here. A different pair of antennas saw the satellite over here. And so what you're getting into is this complex interaction between the way we observe and how these guys transmit. And so eventually you get to this sort of situation where we can model what we should see. And the results are very consistent. So there were no particular surprises. And so up here, we're in Janskis here. So you see we're kind of getting up to about 10 Janskis here, which is still less than the signal that we all generated on Pluto together. And so it's significant. But it's very brief. These satellites pass across the antenna in sort of 90 seconds or something or other across the site. And so we did a lot of observations. The results were that the interference from the satellites was kind of predicted and seen. We could detect them. It's very different for something like Green Bank, which, as I mentioned, is a single pixel. It kind of eats everything. And so it is a much more sensitive radio detector that way. The downlinks were detected, but the system doesn't saturate. And that's one of the problems we have, is a very strong interfering signal kind of saturates the system. You lose the linearity in the system, and you can't do scientific observations. So the result here was that for the interferometers, for the VLA, there was complex interactions with no saturation. The user terminals, which are 3 watts, I think, are not much worse than your cell phone, 3 times your cell phone in that sense. And so they were not particularly problematic. Once they're actually not in the line of sight to the radio telescopes, it was okay. So just in general, these results were consistent with the models. We put together some fairly complex models to describe what we were getting, and it all kind of hung together. But, thinking about the future, if there are more satellites, there are different satellite systems, they're all transmitting on different things. This whole thing about connecting to cell phones, which kind of appeared, we started to think about, is it possible to actually really coordinate with these systems? So can we have sort of spatial and frequency sharing schemes? Can we actually connect the real-time system so that the real-time system that's driving our antennas actually knows what SpaceX is doing? And so if there are antennas flying, they're satellites flying over the site, and we're not observing at that frequency, do we care? These are the sorts of ideas that have been floated around. And the goal here is really to preserve our protected bands. If we can control their interference on us better, we can do more science. But it also potentially opens up some lost frequency for us, and it opens up the bandwidth for them. It might be possible for them to get back into that lowest band that they had to not transmit into to meet the ITU regulation. So we've been underway with a research program with SpaceX, and we've got this kind of concept of radio zone multiplexing. So we essentially know what each other are doing, and we kind of avoid each other. So as the satellite kind of flies over the site within some radius, it goes into the satellite goes into a different mode of transmission. It avoids certain channels, or it basically moves between set channels on a time grid that we know. And so we can then teach our correlator to know about that and blank all of the data when the satellite is on. So we actually did tests of this in the middle of last year, and it worked pretty well. So that's great. It works for SpaceX with 2,000 satellites. Will it work for 5 companies with 10,000 satellites? And I think that's kind of, the challenge ahead for us. And these are just sort of what the results look like, where this is sort of, again, frequency along the bottom and time up the left-hand side. And so you can kind of see on different baselines and in different channels, we made the prediction of what we should see, and we can extract their signals out of the data and so on. So this was very successful. And, we've had a very good collaboration, I would say, with SpaceX. By and large, in a corporate sense, they're sort of aware that they could cause a lot of trouble and we could kind of stop them in their tracks at some level. They don't want that. But I do think there's a genuine sense that they want to be kind of doing the right thing and they can get the job done. If we can work around each other, then we should certainly do that. So in terms of this sort of spectrum sharing, the negative impacts to radio astronomy are growing. There are more companies and more satellites and so on. We're trying to define this constellation standard interface and interaction that could be adopted by the satellite constellation industry as sort of a standard. And that would, I think the advantage is it gets us out of their hair, basically. If they adopt this kind of technique in above radio astronomy locations around the world, then they simply we will not be interfering with each other, and so that's a better place to be. The testing we've done so far in terms of their real-world impact to us, at least Starlink's real-world impact to us, is pretty consistent with our models. As I mentioned, the interferometers are less susceptible to satellite interference. In future, there's other mitigations that can be considered. As I mentioned, a dark secret of radio astronomy is we don't tend to deal with interference. We don't try and recover it. We don't try and do a lot. If it saturates the system, we have to put in a filter or something like that. But generally, we kind of work around it. And we are sort of approaching the point where that will not be possible. And so thinking about ways to design our systems in future is an important part of dealing with this problem. And so just in general, we think it's very important to explore the impacts. Part of what you all fund astronomy for is for us to solve problems. So just sitting there whining about it is not good enough. There are technical problems here to be solved. And so that's kind of the challenge that we're trying to rise to. We have plans for the future, and in potentially the impacts of these satellite constellations need to be noted on these plans. One is that some of those telescopes I showed you, we want to kind of combine those and essentially increase by a factor of 10 the number of antennas we have. So this is the next generation very large array where we would take the current VLA, which would be sort of on the scale of about this guy, build this 5-arm spiral, continue that spiral out into Mexico, Arizona, and Texas, and then combine it with the antennas on the VLBA. So this is, the VLA is 227 antennas. This is 263 antennas distributed essentially across our sector of the Northern Hemisphere. And this is the type of science you can do when you build an array like that. You can actually, I showed you that star forming region earlier where that yellow dot in the center was the size of our solar system. With the NGVLA, we can actually get down to terrestrial scales. And so what you're looking at here is the formation of planets on the scale of our solar system, on the scale of our planets. And with our telescopes in spectral line mode, we can actually look at molecules. We can look at the components of what's forming these planets. And so you can see water and you can see organic molecules and so on. So with these sorts of instruments, 15 years from now, we can actually watch planets forming around nearby stars, and we can measure the chemistry of the gas nebulae that are collapsing to form those planets. And it gives you a lot of information about the formation of life and what the opportunities are for life around some of these systems. So this is one of the science goals of NGVLA, and there are lots of others, but this is the cool one. Another thing we've been doing is getting into radar. We built a radar transmitter for the Green Bank telescope, and at the moment we're receiving it with the VLA and the VLBA. So this is a 700-watt system. I'm pretty sure there's more than 700 watts sitting on the table in front of me there right now. This was a pretty low power system, but we had a lot of collecting area to receive the system. And this was one of our first pilot observations. This is actually the Apollo 15 landing site. Some days we convince ourselves we can see the lander in this image. And so you can end up with like 1.5 meter resolution pixels from something like this. This was the Tycho crater. Again, this is 5-meter resolution and so on. So moving forward, both in terms of the environment we're seeing from industry, but also our own environment, it's more complex. We have plans to build essentially a space domain awareness system where we have a transmitter on the GBT. We transmit out of that guy probably 500 kilowatts or something like that. So we're transmitting 500 kilowatts out of the National Radio Quiet Zone. That's a thing. And then you bounce the signal off the target, and it can be a satellite, it can be an asteroid. You can do sort of solar system research this way. You collect the reflected signals in the sort of multi-static array configuration, and then you rebuild some image of the object, be it a satellite or an asteroid or something like that. So we are headed strongly in this direction. The design of that transmitter is underway, and hopefully one day, some years from now, we'll have this high-power transmitter at Green Bank and being received by the NGVLA. So just in general, I've sort of given you some sense of what we do and how we see the sky. And a lot of the time, the sky is like this. It's some antennas, and you're looking at a quiet sky, and we are really sort of fundamentally doing scientific research. And this is why we build these antennas, and this is why, there is international frequency regulation and so on. I noticed actually this morning, this one is not perfect. There is a plane or a satellite trail in the middle of it there. But a lot of our astronomy is still like this, and this is why we go to these remote sites and so on. But the future is changing, and we certainly need to be able to deal with things. So this is a video. What I'm about to show you is a video we took at the VLA site a couple of weeks ago, actually, and it was just kind of cool, but it kind of gives you a sense of what we actually deal with in the real world. Right, there's lightning storms, and you see all these planes whizzing over, and then you see some satellites whizzing over. And amongst all of that, we are still doing our astronomy. And so in some sense, that's what the interference of these constellations is going to look like, that we are going to have to continue to develop technologies, develop ways of processing the data to be immune to the impacts of some of these other sorts of effects. And that's really where all of you come in, that the digital work that you're all doing and the types of technology you develop. Ultimately, we are an incredibly interested customer and hope to work with you more in future. So thank you.
Is it on? Testing. Yep. Testing. Thank you. Are there any audience questions for Dr. Beasley? Are there any plans to do radio astronomy from space, so something like a James Webb, but instead of optical radio astronomy?
Sure. So, I mentioned this idea that we do interferometry, and the resolution of the image depends on the separation of the antennas. So we have built systems in the past where we had a radio antenna in orbit, and we, again, it has an atomic clock on the spacecraft. We capture the data and send it back down, and we've used that like a sort of moving, distant antenna. It's kind of hard to support in long term. Eventually you run out of propellant and so on. There are so we have done some of that. There have been 2 major experiments doing that, and then there's a lot of interest in the far side of the moon. And so if you kind of think about the Earth-Moon geometry, here's the Earth, and it's transmitting a lot of stuff, and here's the Moon. There's a sort of cone on the Moon where you can't see any of this Earth-generated interference. And so there's a lot of interest in doing work, in that region. That's hard, getting to the far side of the Moon, doing something, not polluting the environment, getting the signal back, all of that is hard. So there's some interest in it, and there are some scientific goals that might be better done in that environment. But our telescopes are heavy, and getting them into space would be bad. So yeah.
Yeah, good morning. You commented on trying to work out, I guess, a coordination arrangement with the NGSO or the LEO satellites. So for for the geostationary satellites, they're using the same spectrum, or Starlink is using some of the same spectrum as and they also have rules about, especially when they're going around the equator, the LEOs are going over the equator, that they're supposed to turn off or not radiate certain bands because they could be in the line of sight of antennas or terminals that are talking to geos. Or have you consulted those rules, or?
No, it's the same, but it is the same general idea. That's right.
Right.
So obviously the geostationary ones don't move, so it's kind of a fixed problem. Once you get it kind of set up, you're kind of done. There are certainly already regulations on some of the orbiting satellites. Yeah, when they go over some part of Southern Africa, they do not transmit in some band because there is something receiving there or something like that.
Right.
Really what you're talking about though is kind of a change of scale. I mean, if you believe the models, and as I said, I don't really believe the models, but if you imagine you're standing at the VLA site and there are 300 SpaceX antennas above you, so we can coordinate with SpaceX and probably do something meaningful, and OneWeb, and Kuiper. And then, of course, the reality is the Chinese are going to build their own system as well, and they may or may not play, right? And so that's where you've got to kind of attack the problem from multiple things, try and coordinate with them, trying to find standards and so on. But then we need to build hardened systems. We need to be more robust to it.
Right. But I guess there's like a set of rules that are in place, kind of like a standard for NGSO and GEO satellites. And it seems like that a lot of those could be applied. So that way you would.
Yeah, but the rules aren't great, right? In the sense that, if there is an ITU international rule.
Right.
And then the FCC and the NTIA produce their sort of local version of it. In reality, commercial companies have a lot more sway in that process than the scientists do.
I agree with that.
Yeah,
I agree with that. But it's like it's a basis, though. If you're trying to get a standard and trying to make it easy, then
and there is some interest in that. So I think we're trying to define a pragmatic standard, and then we will try and operate it through those channels. Yeah.
Thanks for the talk, Tony. Well, from the Hat Creek Radio Observatory. As we start putting cheaper and cheaper electronics into space, is there ways in terms of regulating the RF leakage of such electronics in space, or is there thoughts on doing that?
Well, if we go all the way back to the diagram, this is going to be slow. If we go back to the FCC diagram, I mean, there are already fixed, there are already fixed bands for the uplinks and the downlinks of space-based technology. So any of you that are involved in CubeSat experiments and so on, the hardware that you use is already coupled to some standard about what you can and can't transmit down in. So interestingly, it's not necessarily the job of the end user, the application developer to do that. I mean, if you have some idea, I believe, if you have some idea of something you want to do in a CubeSat, you're going to buy a standard CubeSat from someone who's going to have standard comms in it. Those standard comms are developed to be consistent with these rules and those standards. So unless whatever your application is, unless your experiment is producing radio signals for some reason or something like that, and that could be leaking over into one of our bands, generally, it's not so much of an issue. It is like in the constellations, it's just the volume, it's the number of them, and you're getting these complex signals coming into the side lobes of the telescope and so on. So I think if you, in general, for these applications, you're buying standard communication systems to go in your spacecraft and so on, usually it's okay. But then, as I mentioned, that by and large, over the course of 20, 30 years here, we've sort of got to the point where it's very hard for us, and we generally don't go hunting for signals around, downlink bands, because you're just going to get crushed. So this is a little bit of a problem for us in sort of that radio galaxy astronomy sense. It's a big problem for the SETI people, because they're trying to be somewhat agnostic to what we're actually looking at. And so if you're anywhere near 12 gigahertz these days, right, DirecTV is blasting you. So it's not a particularly productive place to go hunting for radio astronomy either. So just in general, I think, if you're using standard components and you have space applications, probably you're not part of the problem, certainly for one CubeSat or something like that. If you put up 10 million CubeSats, that might be more interesting for everyone. But if your application somehow has a non-standard transmitter on it because you're doing something, I don't know, Yeah, that'd be something we'd be interested in. But again, you ultimately have to have an FCC license for it. There is a well-defined review process. We would get to write a nasty letter about you, so it would be okay. That said, coming back to the previous question, our nasty letters are not that nasty, and in general, FCC perhaps doing the job that it should is trying to push commerce and move things through. And so we fight a lot more than we win. Yeah.
Got time for one more question.
Hello. So yesterday we had a talk with the director of DARPA, and she talked about their project Space Bacon, which is designing a reconfigurable terminal to allow the different constellations, LEO constellations, to communicate with each other. And I'm with Arizona State, and we're working on that project there. And I was wondering if you guys had thought about interacting with a project like that at all ever, where like you talked a lot about how you've worked with Starlink, but something like that could allow you to communicate with more, interact with like more different companies that have constellations out there.
Sure. So we've worked a lot with SpaceX, with Starlink. We've also interacted with OneWeb. We haven't done any testing of OneWeb yet, and Kuiper is further back on the track in some ways. And so, yeah, I was at Stephanie's talk yesterday, and I kind of looked at some of the things she was doing, and it's very difficult for me to assess the reality of it in some ways, right? And you know, that you talk about building a network which is merging those other networks. So it has a cool name and there's a nice diagram, but actually what it means in terms of technology and what are they actually doing, I don't think it means anything in space. I think it's more about technology on the ground coordinating, you know, the transmissions from these constellations, or not, I don't know. So DARPA's hard, right? By definition, it's hard to sort of roll up to DARPA and say, you know, what are you up to? And get some answer out of it. So I did note the talk, and I noticed there was another thing on there where she mentioned correlator systems. And I was thinking, what is that? So I absolutely take your point. We probably should spend more time looking at exactly what technologies are being developed there and so on. But to the general point, and maybe kind of the broad takeaway here, is that once something like Starlink is permitted and is underway, we tend to try and just stay away from it, right? Or find some way to coordinate it with it largely. You know, one of the interesting things is that I guess it's a funding issue. There's an enormous difference in our development cycle time relative to DARPA. You know, you heard yesterday that like it's like 3 years and you're dead or done, right, or whatever it is. So we have National Science Foundation funding. Just in general, the development of one of these telescopes takes 25 years, typically speaking. And so there's a little bit of a timing problem there, is that we can sort of spot the environment, try and build something that deals with that. There'll be 8 cycles of development here. You know, SpaceX will be transmitting at 40 gigahertz by the time we're finishing. So that is a challenge, but point taken, we absolutely, I was intrigued by her talk and I should follow up on that, yeah. Okay.
Hello? Okay, so before we let you go from stage, so last Sunday, I learned what a challenge coin is. I assume you know what a challenge coin is, right?
A what?
A challenge coin?
A challenge point, no?
A coin? No? A challenge coin?
No.
I see. So you're not from the US like me. So I learned about these on Sunday. So I'll let someone else educate you. But they're basically tokens of appreciation in a sense. And we have a rare set of 3 challenge coins for our distinguished keynote speakers. We'd like to present you with one of those as a as thanks. And with that, I'd also like to ask for a big round of applause for Dr. Beasley.